Hi, I'm Lauren Gold, and I'm presenting our work, Planetary Visor. We use virtual reality to show data collected from Mars instruments, combining orbital and ground-based perspectives. Planetary Visor is a tool to visualize planetary spectroscopy through immersive on-site rendering. In recent years, satellites orbiting Mars have captured unprecedented volumes of data. These images and spectra have mapped the red planet and revolutionized our understanding of Martian geologic history. On NASA's Mars Reconnaissance Orbiter, one instrument called XRISM measures the reflectance of the sunlight off of the surface of Mars with respect to wavelength. Comparing the received spectra against spectral signatures of known materials helps us identify minerals on the Martian surface, including those formed in ancient environments under wetter conditions. Meanwhile, NASA's fleet of Mars rovers, including Curiosity and recently Perseverance, are mapping the terrain from the surface. These rovers see the Martian surface with much finer detail, but can't cover nearly as much ground as can be observed by the orbital instruments. These two approaches are complementary, but the data are rarely shown in the same visual space. This makes localization and scaling challenging. For example, XRISM collects spectral pixels as it flies over a target, but each spectral pixel covers a roughly 18-meter footprint on the Martian surface. That's larger than an 18-wheeler. And where is that footprint? What is the shape of that footprint? Where does it intersect with the rocks, dirt, and complexities of the terrain as seen in the rover scale imagery? To get at this, Planetary Visor combines the data sets into a single visualization. The user can stand on the surface of Mars and see a variety of data sets at their fingertips, derived from rover and orbital instruments. We give a handheld tool to the user so they can select and see the shape of the spectral pixel footprints among the rover terrain. They can simultaneously see the spectral reading on a handheld plot. To change their scale, they can use a grab-based gesture to turn themselves into giants on Mars to get contextual views or navigate around. Or they can revert back to one-to-one scale. If they want, users can use external GIS tools such as ArcMap or ENVI to prepare their spectral data with the types of processing workflows that they're familiar with. This generates the input data for our system. The data cube contains samples of reflectance. Each sample has hundreds of channels of wavelength and is indexed by where the sample is in the line and the order in which the line was taken. So all of the reflectance values are indexed by X, Y, and lambda. This is accompanied by a corresponding data-derived record, DDR for short, that maps the XY index to latitude and longitude coordinates. Planetary Visor uses the data cube and DDR data to place spectral pixels among the Martian terrain and to plot each pixel on the spectral plotter when it's selected by the user. We shape the spectral pixel footprints into a polyhedron that intersects with the terrain and points to the orbiting spacecraft at the time the observation was made. This gives the planetary scientists a representation of where each spectral pixel physically intersects with the terrain material that it reflects from. We conducted a user study with 8 experts in planetary geosciences, including experienced members of rover operations teams and orbital data scientists. We sent them Oculus Quests and sat on Zoom calls with them, walking them through the different functionalities of the Visor system while they gave us feedback in our IRB-approved study. We also had a questionnaire whose results we talk about in the paper. Some highlights of their feedback include the following. It's easier to maintain good sense of scale when navigating the terrain compared to traditional tools. And the 3D view makes it easier to interpret geologic features as compared to 2D or desktop 3D representations. And users claim to have gained a new perspective and more geological context of the orbital data. They also provided some great ideas for future work. We're currently working on implementing new tools to address their suggestions, such as incorporating more rover datasets and exporting spectral plotter compositions and comparisons for offline viewing. Moreover, the system can be extended beyond the current location and datasets. We can build a similar environment for the landing site of NASA's new Perseverance rover. We can also use new and improved orbital remote sensing data as they become available, even thinking beyond Mars to the Moon and other planetary bodies. By combining orbital and ground-based datasets into virtual environments like Planetary Visor, we can immerse planetary scientists in the data they study, giving them new perspectives towards new discoveries.